Her research interests span various fields, mainly combinatorial optimization, stochastic programming, and multi-objective optimization. She has made various contributions, many contributions, which are, I would say, at the forefront of the effort to develop efficient combinatorial optimization methods for stochastic models, so stochastic problems. So I'm very happy very happy that she accepted the invitation to present during this workshop. So Merve, you have the floor.
Thank you very much, Walter. It's truly my pleasure. So first of all, I would like to thank you, Eric and Fabian, and everyone involved in the organization. This is a wonderful, wonderful workshop. So it's a true pleasure to be here with this great group of people. So I'm looking forward to also interacting more with everyone during the breaks. All right, so let me get started. So please feel free to interrupt me. I will try to keep my eye on the chat screen, but if you also have any questions during it all, feel free to unmute and speak. Just feel free to interrupt me at any time. So today I will talk about Lagrangian dual decision rules for this very complicated class of problems, namely multi-stage stochastic integer programming. By the way, you will also be seeing my color palette there. I wanted to be safe, so I just connected my iPad and directly sharing my iPad screen. So sorry about that if it's a little bit of a distraction. Okay, so this work is actually, I will present rather than just one work, just to give you an idea about the potential uses of these new decision rules that we are going to talk about. So in that regard, this is a truly multi-stage collaboration. So this work actually is inspired by my discussions with Jim, actually, and then especially based on our previous work on two-stage linear decision rules that I will review shortly. But then we involved my PhD student, Meryem Daryalal, who's a last year fourth-year PhD student right now. And also in terms of different applications, I involved some other students. So Changwa, who was formerly a PhD student of mine, who is joining Clemson University now. And then Anna Deza, who was an undergrad student here. She's currently a PhD student at Berkeley. So this is truly, it already has a multi-stage flavor in it. But what I want to say is, yes, the talk is about this complicated multi-stage stochastic programming problems. But if you look at my somehow scenario tree looking collaboration tree here, if you like, it doesn't look very much like a proper multi-stage scenario tree, right? So it truly looks like, oh, I just branch one time here. So it really looks like it's a two-stage stochastic programming scenario tree I have. And in that, exactly this is what we will be doing. So in this work and many ideas that I will talk about today, our motivation will be collapsing our multi-stage stochastic programs into two-stage ones, because for this class of problems, as for instance, we've seen in Jim's tutorial yesterday, we do have a lot of suitable, efficient methodologies that we can leverage. So that will be our game plan, collapsing everything with the help of these decision rules into a two-stage setting, and then leverage everything, all the hardcore tools that we have in that simplified, reduced setting. All right, so what are two-stage stochastic programs? We all know now that, of course, there are the uncertain parameters that are modeled as random variables. So we know they're associated probability, joint probability distributions. And in the two-stage setting, we have two decision-making stages. And the first stage decisions here, they are deterministic. They need to be made right now without knowing the actual observations of these related uncertain parameters. But once we get to observe them, we get to make second time a set of decisions, namely our recourse second stage decisions. And the most commonly used form of an objective in stochastic programming is this expected total cost or profit, if you like. So I will be talking about minimization. So my goal will be minimizing the deterministic first stage cost, whatever you incur right now, plus whatever you expect from the future, of course, in the form of an expected value. But now let's extend this to multi-stage settings. So now we end up with these finite horizon sequential decision-making problems under uncertainty. Rather than two decision-making stages, we will get to make decisions t times. And I will be using this bracket notation to denote the set of integers from 1 to t. So in this multi-stage setting now, rather than one set of parameters, uncertain parameters, so psi subscript t is denoting this vector of parameters on random variables associated with stage t, but we have many of them, one such vector per stage. So in that regard, we will be putting all of them together. So this set of random vectors will be describing our underlying stochastic process. I will also be using this superscript notation, and thanks to actually Francesca, my notation aligns very well with what she's been using earlier this morning. So the superscript version of the psi t will denote the whole history that we observe, everything we observe up to our decision-making stage T. So that will be our history superscript version. So in terms of decision variables, now what we have is all this decision vector xt to be made at stage T, it is a function of the whole history to be observed up until then, because our random variables size are there random, it makes our decisions actually random variables themselves. But one important property that we have is our decisions are non-anticipative, meaning that they only depend on the history that you observe up until that point, not your future decisions and observations. Right, so we have these non-anticipative decisions, and most notably, the decisions to be made at the very first stage, they are deterministic. And for convenience of the notation, I'm still gonna parameterize these guys with a psi1, but psi1 will be fixed to 1, which indicates that my first stage decisions are deterministic. So this is a very, very generic version of a multi-stage stochastic programming model. Without loss of generality, any sequential decision-making multi-stage stochastic programming model can be put into this form. So in our objective, we are minimizing, as usual, in the risk neutral setting, we are minimizing the expected total cost, the summation over all the stages. And here the expectation is taken with respect to the probability distribution associated with our stochastic process, this full, basically all of them, this is capital T. So we are minimizing total expected cost. In terms of constraints, for every stage T and for every possible future sample path, basically almost surely, we have to satisfy two types of constraints. The first of those are known as state equations, because basically what these are doing is these are linking our previous stage decisions to our current stage decisions. So this is the glue between different consecutive decision-making stages. So these are state equations. And we also have these local constraints. So everything that is associated solely with a particular decision-making stage T. So in that regard, that feasible set associated with stage T decisions, we will be denoting them with this capital X of T. And note that we could very well have mixed integer decisions, in other words, mixed integer recourse in this generic multi-stage programs. So if you look at the literature, of course, like there are a lot of progress lately on the multi-stage stochastic programming, especially the multi-stage stochastic linear programming. We have a bunch of good tools out there, but many of the existing approaches, they rely on this scenario tree model of the uncertainty. So this is one particular approach that you can take, but the main difficulty, main challenge with this type of a scenario tree-based approach is, in order to get even moderately accurate approximations to the true problem, you need to build an exponentially large scenario tree, exponential in number of decision stages. So this difficulty can be alleviated if you have certain assumptions, such as stage-wise independence, which means every random vector of the stage has its own distribution, has its own independent set of realizations. Under that, you can maybe do a little bit better. For instance, you can try to use this stochastic dual dynamic programming extensions for the integer setting, although we are still like in the development phase in this case. For LP setting, we have STDP, which works great for the scenario tree approach under stage-wise independence, or you can think of, again, some extensions where you can handle, for instance, binary state variables or multi-stage generic stochastic programs with Lipschitz continuous type of value functions. But nevertheless, these approaches might also have slow convergence. So in that regard, we will take the completely different avenue from this literature. So one is you can use scenario tree to basically approximate your uncertainty in a simplified structure manner. On the other hand, in the decision rule approach, we will give that freedom to the uncertainty model, so we can work with sampling type of approaches, but we will this time instead restrict the form of our decisions. So we will only be allowing ourselves to choose from a particular family of structure decision, basically policies. So I would like to quickly review the literature in terms of the especially linear decision rules, but for starting with multi-stage stochastic linear programs. And then in this talk, this will be the main theme of this talk, is we will extend their use into integer setting. So let me start with primal version of these linear decision rules, in short, LDRs. So the idea is we will restrict our decisions at every stage, every possible decision, to be a linear, or rather a fine function of the history that we observe up until that point. So, and once you do that, when you restrict all of your decisions in that manner, that will collapse your whole multi-stage problem into a static one. So here's what's going on. So this is our multi-stage stochastic program, basically, and note that every decision here is, they're unanticipated, but they still depend on the whole history. They are potentially these infinite dimensional objects, but then we will apply these linear decision rule type of approximations, restrictions to our decisions. We will say that this set of decisions that I will make at stage t, which are parameterized by my history up until that point, they cannot take any value. I have some specific requirement on what type of values I can have for these decisions. Namely, they need to be, you take this history up until that point in a matrix form, and you multiply it with this new deterministic decision variables. I will refer to them as LDR variables. So we will be introducing these new set of but deterministic decision variables. I put them all into this calligraphic XT matrix form, and these deterministic variables that we will decide on, when you multiply them with your observation history vector, they will map you what your decisions should be. So we are heavily restricting our decisions in that form. But what is a good thing about it? Once you apply such a restriction for all of your decision variables, then your multi-stage problem collapses into a single stage problem. Now the only decisions that we get to make are these LDR rule decision variables, and they're all deterministic. As such, we end up with a deterministic, in other words, single stage static problem. So you can actually play the same game for multi-stage stochastic linear programs in the dual setting. If you have a multi-stage stochastic LP as well as the primal, it has a dual version, which is another multi-stage stochastic LP. You can apply the same type of LDRs on the dual variables, and you can also obtain some lower bounds from the dual side. So Jim and I, we extended this idea to these two-stage linear decision rules. So in this case, the difference is we don't want to apply these restrictions on all of our decision variables, but rather on a subset of the decision variables, which collapses our problem into now a two-stage rather than a single-stage problem. So what is this subset of the variables? I'm not going to be able to get into details, but these guys, basically, you need to distinguish your decision variables as state variables and local recourse variables. And if you apply these LDRs only on the state variables and free the other recourse variables, don't apply LDRs on them, then you will end up with a two-stage stochastic linear program for which you can apply bandage decomposition type of algorithms and efficiently solve them. And more importantly, you can leverage sampling ideas. You don't have to restrict yourself to a scenario tree form. All right, but we are talking about affine rules. So in that case, what about my decision variable xt, for instance? It has to be integer value. I cannot say that it can take any continuous value that can be mapped from these LDRs. So unfortunately, these LDRs don't directly extend for the integer case. And moreover, as I mentioned, the dual side, both primal and two-stage linear decision rules, you can apply them on the dual side of the linear programming version of the multi-stage. But if you have integer multi-stage programs, there's no LP duality. So, but we have some other duals, and that's our key idea in this first work, is why don't we use a different dual, namely a Lagrangian dual for a multi-stage mixed integer programming model, and apply LDRs to those duals, basically Lagrangian multipliers. So that's the key punchline idea here. So in order to be able to put this idea in practice, we are going to make two assumptions. The first one is we are assuming that these set of constraints associated with our local stage decisions, they are bounded, compact, in such a way that we are ensuring that we will have always dual feasibility in our application of these LDRs on the Lagrangian dual. The second assumption is for the sake of primal feasibility, especially if you are going to employ our suggested policies in a rolling horizon framework, you need to ensure that whatever decisions you made and whatever observations you have so far, you always be able to make your next set of feasible decisions. And this is a very, very standard assumption, namely it comes in this form of relatively complete recourse. So what are we going to propose exactly? We will propose two different Lagrangian duals, namely the stage-wise SW dual, where we will relax these state equations, the ones linking consecutive stage decisions together. And the second one, I will first tell you guys, although I believe many of you are familiar with it, this reformulation of the original multi-stage problem, namely the non-anticipative reformulation. And we will consider these so-called non-anticipativity constraints from that reformulation and relax those in a Lagrangian framework. All right, so before I get to the details of these two duals, here's our full general framework, what we are suggesting in the solution methodology. So basically, what we have is we are given this multi-stage mixed integer programming model, And first, what we will do is we will find either we will use its original reformulation that I showed in the general form, or we will consider it as non-anticipative type of reformulation. But whichever formulation you start with, we will relax some constraints and we will get this Lagrangian relaxation of our model. And then we will apply linear decision rules to those Lagrangian multipliers that we defined. And now that we have this Lagrangian relaxation problem, as I mentioned, it is going to, because we are applying LDRs on the dual variables, it collapses into two-stage problem, which we can solve with our favorite approach, for instance, sample average approximation. So for that two-stage problem here, we will get a set of scenarios, for instance, and solve this two-stage problem. And as a result of which, we will get some LDR decision variable solution. So that will be our key output from the methodology. But if you look at the objective value of that two-stage problem, it means nothing. To make sure that we are getting statistically valid lower bound, we will get another so-called evaluation sample and plug in our evaluator, this LDR solution and this new sample, and we will find a confidence interval on the lower bound for our true optimal objective value for a minimization problem. So I will also introduce today two types of primal algorithms that we came up with that are going to be all guided by these LDR decision variable outputs. And through those, in a rolling horizon framework, we will again evaluate our potential future scenarios, and we will also build a confidence interval on an upper bound of on the true optimal objective value of our multi-stage problem. So this is our full picture. So next, I will tell you more about these two particular duals that we will use in this Lagrangian framework. All right, the first one is this stage-wise Lagrangian relaxation. So here I start with my original multi-stage problem. And what we will do in this one is we will focus on these state equations, and we will introduce these dual multipliers for them, pi t for each one of those constraints, and we will relax them, put them into the objective by penalizing their violation if they are violated. So one thing that I would like to note here is that these dual multipliers, pi's, they are functions of the history themselves, because here we have these constraints for every possible sample path. So in that case, these pi guys, they are actually infinite dimensional, difficult to work with type of objects anyways. But for the time being, just assume that I have them as in the form of these policy. So I gave you what type of a policy I have for these pi functions. And once you fix those functions, then you can do this relaxation. Basically, you relax our state equations and add them to the objective in the form of expectation. So I can work with this type of a Lagrangian relaxation. So what is good about this relaxation for, again, given set of dual policies is if you look at this objective and it is most notably constraint set, now you will realize that there is nothing linking. You can rearrange the terms in this objective and have one coefficient for the xt vector, and then you will realize that there's nothing linking consecutive x decision variables anymore. As such, this problem can be actually decomposed by stage t and sample path. So if I give you again this fixed set of dual policies, you can solve this problem by just sampling, and for each scenario, you can basically solve a deterministic mixed integer program, especially if one in parallel, so you can do this by means of decomposition very efficiently. All right, so this is where we are at right now. This is our Lagrangian relaxation. Again, if I give you a particular set of dual multiplier policies, and if you solve this problem for a fixed pi selection, then you will get a lower bound on the true optimal objective value. But what we are seeking for is truly the best of those lower bounds. So as such, we are trying to maximize our lower bound by making our smartest choice over these dual multipliers. So this is our Lagrangian dual problem. But as I mentioned at the beginning, these guys are very difficult to work with. These are random variables themselves. These are functions of history. These are, again, potentially infinite dimensional objects. So with the help of these LDRs, we will actually get rid of that difficulty. So basically, we can overcome it by restricting our dual multiplier, for instance, this pi t variable as a LDR. So here what I have is these betas will be my LDR decision variables. These are the deterministic variables that I'm introducing. These are parameterizing by my linear decision rule. And here I have a little bit of a general case. Before I was just using the history. Now on top of the history, I added this function, which we call a basis function. So basically, these are just functions that will give you will give the history, and it will output you a bunch of numbers. And for each of those numbers, we will multiply it with our LDR variables, and whatever result that we obtain, this is going to be our pi to be used in the policy. So here's a quick example of 2 examples of these basis functions. Say I'm at stage 3. So this basis function, this basis function, for instance, can return, assume that I have a single random variable, psi2 and psi3 per stage, then it could very well just return you whatever you observed exactly. So it could just return you the random variables themselves. If so, then you will say, I have this multiplier 1, psi2, psi3. I will multiply them with my deterministic variables beta. This is going to be my restriction for this pi3 variable. But if you want to involve more information from the history, for instance, in addition to those 3 existing random variables, you can say, I'm going to make up a 4th random variable function, this basis function, psi2 times psi3. As such, you will include another decision variable, and hopefully it will be a little bit of a more flexible decision rule for you. But this basis function selection is a very, very interesting, I would say, future research topic, how to choose them wisely to get the best solutions, best balance to your problem. Anyway, so what we will do is we will enforce these linear decision rules on our Lagrangian multipliers. And now that I do that, I don't need to optimize over these infinite dimensional crazy policies, pi's. I can instead just simply optimize over my deterministic parameters, decision variables, betas. So this is what we end up with. This is what we are calling our restricted Lagrangian dual problem. All right, so second dual that we have is it's going to be depending on this reformulation of our original multi-stage stochastic program. So let me first introduce you the notation to be used in this non-anticipative reformulation of the true problem. So in this formulation, we will be working with these so-called perfect information variables. So I will be introducing this set of variables y that are now functions of the whole sample path rather than history up until where you are at now. So even if I'm at stage 1 or even if I'm at stage t, I am going to parameterize them with my capital T, last stage, in other words, the full sample path. So that's why these are actually anticipative type of decision variables. So, and then for those anticipative type of decision variables, I will define their corresponding constraint set, feasible set. So they need to satisfy the state equations as well as our local constraints. So the only thing that is missing is non-anticipative. These guys are anticipative. But we can actually do this with the addition of this last set of constraints into our reformulation, which are going to make them non-anticipative. So these are called non-anticipativity constraints or inconsistency constraints. What they are trying to say, this is a compact version of it. There is also a pairwise version that is easier to interpret, but you can think of it as for every stage, you are trying to make these anticipative decisions. They depend on the full scenario, if you will. But if conditioned on the fact that your different scenarios happen to share the history up until t, then those decisions should be exactly the same. If you came to this point in your scenario tree, for instance, if you think about exactly the same, but your future has a bunch of different options, you don't care. If I observe the very same history up until now, my YT decisions at that point should be exactly the same. In other words, they have to be non-anticipative. This last set of constraints are doing that basically. All right, so now we have our reformulation of the true problem. So now let's apply Lagrangian relaxation on top of that, for which we will introduce these Lagrangian dual multipliers. Again, this policy form infinite dimensional objects, gamma t for every potential sample path. And then we will get these constraints and push them to the objective. So let's do that. Let's push them to the objective. So now for a given, again, set of Lagrangian dual multiplier policies, I have this Lagrangian relaxation problem. So as you can see from the previous one's inspiration, this is also nice. This is also decomposing, but this time, this only decomposes by scenario, not stage. So in that case, I can still, for a given set of policies, Lagrangian dual multipliers, I can still solve this by means of decomposition efficiently, but now every one of my subproblems, they will be this T-stage deterministic though subproblems for each scenario. So still you can solve this relaxation pretty efficiently. So if we solve this relaxation for any given choice of multipliers, we get a lower bound, and Lagrangian dual problem is seeking for the best lower bound you are maximizing over your choice of policies. So again, these gammas, Lagrangian multipliers in the second case, they're also difficult to handle. As such, we will again make our jobs easier, and we will restrict them by applying linear decision rules. So here, this time I'm using alphas. I was using betas for the stage-wise dual. For this one, for the LDR deterministic variables, I'm using alphas. And for the basis functions, I have these phi's, the same thing. You just apply, restrict your Lagrangian multipliers gammas to follow this affine form of the full sample path history. Okay, and then if we apply these rules, then our Lagrangian restricted form of our Lagrangian dual problem is looking for the best lower bound, but this time it can only choose our deterministic LDR variables alphas, among which we will find hopefully the one giving us the largest lower bound. So we have two different relaxations and accordingly two different Lagrangian dual problems that are restricted with the help of linear decision rules. Can we compare these bounds that we will get? Okay, so forget about the restriction LDRs for a second. So if you look at the original Lagrangian relaxations, we know from the literature that non-anticipative dual cannot be worse than the stage-wise. It can usually give you something much stronger. But if you try to follow the proof of this one, unfortunately, it doesn't immediately go through for our restricted, LDR restricted Lagrangian duals. So that's why we needed to do a little bit of more work. But luckily, we were able to show the similar result, as in our restricted non-anticipative dual is at least as good as the stage-wise one if you choose your basis functions carefully. So what this theorem is saying that if you already committed to a set of basis functions for the stage-wise dual, then if you choose the basis functions accordingly, carefully for the NA dual, so that like you are giving it a fair chance, you need to give it enough of an information so that it also has the chance to use the same information, leverage the same information. If you get to do that, then NA dual can give you something better than the stage-wise dual, and it's never worse. Okay, but we are interested in their computational performance. So that's why I will also explain our primal side of the story and then show you a bunch of computational results. So this is what we've seen. We talked about how to build our relaxations and apply LDRs there. And as I already mentioned at the beginning of the talk, now that we have our LDR restricted Lagrangian dual problems, these are technically two-stage stochastic programs. For instance, we can solve by means of sample average approximation. Then you can do a cutting plane algorithm. For instance, if your second stage happens to be LP, then you can use bandless decomposition. And in fact, in our experiments, we are mostly using regularized version of bandless decomposition. But one way or another, you solve these LDR restricted Lagrangian problems, and from either stage-wise or the NA dual, you get these candidate LDR deterministic decision variable solutions. So we get our LDR solutions as an output, but the first thing we should do is we should take an evaluation sample, potentially much, much larger than what we used in the solution phase, and evaluate the true performance of these decision rules for the sake of the basically lower bounds. But next, I would like to design some primal algorithms that will be guided again by our candidate LDR solutions, so that we can also compute some solutions that we can truly implement in practice. So this is more important. As such, we will also be getting an upper bound. All right, so I will talk about two specific policies, but let me first tell you the general framework in regards to how to actually implement such policies in practice, or how we evaluate them, right? So the general scheme, the most common use of these multi-stage policies are you implement them in a rolling horizon framework. So, and if you also think about the practice, this completely matches what we do in practice. So if you're at the current stage, say t-1, and you did whatever to obtain your policy, so then your policy suggested you at that point with this observed history up until that point. So omega is the particular sample path index subscript. So up until that point, you use all the information, you solved an optimization problem, or you don't care, you made up a solution, your favorite solution, you decided to commit to this x hat t-1. And then as soon as you commit to this one, while you are moving to the next stage, you will get to make a new set of observations associated with stage t, and then we will get to make another set of decisions. So our primal policies will tell us what's going on inside this box, in each one of these boxes, how we get our candidate X solutions as a result of what we know and what we want to do to optimize our total cost, for instance. So the standard approach could be, for instance, one of the most commonly one that is used in practice, I would say, is a myopic policy that you completely ignore the disregard the future. In other words, you are making your best decisions right now without worrying about their downstream cost, whatnot. The better idea would be, an improved version of this one is, let's not ignore the future completely, let's take it into account, but take it into account in a simple way. So what we were doing in this first so-called expected upper bounding policy type of an approach is, we will consider future random variables, what might happen after our current stage, but we will consider them. If I'm at T, I will consider the future only in the form of a single sample path. I will only consider, if you will, a single scenario towards the future. And this scenario will be, in particularly in this specific heuristic, we will build by considering the expected value of my random variables, of course, conditioned on what I observed so far. So I'm at stage T, I observed a bunch of realizations, and using that, I will consider maybe options towards the future, but in a simplified heuristic, you will only consider one so-called conditional expected scenario towards the future, so that in this box, you can be just solving a single stage problem rather than a two-stage, or rather even a multi-stage problem. So our idea would be, now that we have these restricted LDR-based Lagrangian dual problems, and we will get our, remember, LDR candidate solutions, we would like to drive these policies using those LDR solutions from our restricted Lagrangian problems. So in particular, what we will do is, we will consider some of those policies and try to modify them by adding some new terms to the objective, whatnot, or we will maybe expand the deterministic problem into two-stage, but with the help of these Lagrangian dual LDR solutions. All right, so I will review quickly two of those. First one is how we can guide our primal policy using the first stage-wise dual policy. So if you solve our restricted stage-wise Lagrangian dual, you will get these LDR variable solutions, say beta hat, but knowing beta hat combined with our basis functions means we know our actual Lagrangian dual multipliers, what we will use for these pi values. So given this one, what else we know? We also, of course, observe, if this is the scenario that we are simulating, then we also know the history up until that point, as well as what the decision that we made in the previous stage. This will come us especially as a state information. We will have one more parameter rho that can parameterize your policy and maybe give you a bit more flexibility. That's not that important. So how we will get to make our next stage decisions, XTs. So what our proposal is to modify this deterministic problem. So the one that we have from this expected upper bound policy. So I have exactly what we usually have in this expected upper bound policy. We replace the future with this single conditional expectation type of a scenario. And you have these variables for the future, what you will do in the future under that single scenario. But more importantly, I have my XT decisions that I'm truly after. These are going to be the decisions that I will fix and implement, and then I will roll my horizon. So in the standard expected upper bound policy, you only have this original cost associated with XT decision variable. So this is the correct cost of that stage that you will account for actually. But what we are doing is differently here is we are adding a second term for the cost coefficient of this current stage decisions that are guided by this LDR variable solutions coming from our methodology. And I'm not going to be able to give you the details, but if this objective is basically coming from our Lagrangian relaxation problems objective, so there is a reason why we picked it this way. But what I'm trying to say is we just add this new term here, which modifies the cost of the XT, hoping that you will make better decisions if you were also considering the future, which is all hidden in this beta term information pretty much. Okay, so this is a single stage deterministic type of a tool that you can incorporate into your rolling horizon for making your decisions. So the second one will be motivated by our second dual, non-anticipative dual driven policy. So now my LDR decision variables are outputted as alpha hats. And of course, using those, multiplying them with basis functions, I know my corresponding gamma hats, basically Lagrangian dual multipliers. So for this one, again, I'm giving a current history that for the scenario that I'm simulating and my previous decisions, most notably the last one. What should I do now? That's our question, right? So for this one, we are proposing a two-stage stochastic programming model to make our decisions. So this is how it looks like. So what I'm trying to do is, again, I'm trying to choose xt, my current set of decisions, that needs to, of course, comply with our state equations and local constraints. And this used to be, as usual, it is current stage cost, direct cost, that we are now modifying with the second term. So what is the second term is, we will look into the whole future now in the form of not a single scenario, like this expected bound value type of heuristic was considering single one. In this one, we will consider multiple scenarios towards the future and actually do this two-stage stochastic programming approach. So we will consider our scenarios and we will try to also include the expected second stage cost for the whole future. But of course, we are conditioning it into what we have. So if you decided to now xt decisions are your first stage decisions, if you get to apply them right now, what do you expect from the future? But now you have a better idea about the future. So this second stage problem, it's mostly grayed out, so it's not important. I just want to highlight the fact that our second stage recourse problem here, we are parameterizing the objective with these LDR solutions that are coming from restricted NA Lagrangian dual. So again, this is the modification inspired from how this dual problem looks like. Okay, but we have a one-stage type of a tool to make our decisions in a rolling analysis framework, and we have a two-stage stochastic programming model. And of course, because this is two-stage, you can imagine that this will be much more time-consuming than the previous stage-wise driven policy that I mentioned. All right, so I still have a little bit of time, though, so I would like to quickly show you some use cases of these Lagrangian-based linear decision rules in a variety of applications. So the first two works are from our original paper with Meryem and Jim, and we have a multi-item lot sizing with backlogging production leg type of a very standard application example. And then second of all, we have a novel application of multi-stage stochastic programming in a telecommunication related problem that I will describe quickly in the next slide. And then we have a recent work that we are about to finish soon from a healthcare domain, which is distributed operating room scheduling. This is a joint work with Anna, Cheng, and Meryem. And finally, Meryem has been also trying to apply these rules on a service system stuffing and scheduling problem. I just would like to give you some numbers from each one of these applications to show that these Lagrangian dual decision rules, they could be helpful, they could be promising, especially if our community maybe plays with them and improves them a little bit more. All right, so what you can experiment with in terms of the use of these Lagrangian-based dual decision rules, you can definitely analyze your basis function selection. As I mentioned, it could be a very important choice. So you can basically try a bunch of different basis function options and look at the trade-off between your computational time and the quality of the bounds and the solutions that you get. Second of all, you can look into this non-anticipative variable selection, which is important. For instance, Surajit had this very comment in one of his earlier papers that inspired us to look into this more carefully. If you look at your multi-stage problem, then if you enforce non-anticipativity on a certain set of variables, then they automatically imply the non-anticipativity on some other variables. And this is, of course, this is redundant if you think about it in the original problem sense, but for our restricted Lagrangian duals, it makes a difference. So it can impact your bounds, so you can test those ideas. And last bullet point is for your specific problem, of course, you can do sensitivity analysis, but what I will be talking about today, giving you some numbers in regards to these bound comparison. So how are our obtained lower bounds for minimization problems, as well as how are the quality of our primal policies. So I will give you some bound comparison, in other words, for these two duals, and our reference points, our reference points in that regard will be these two things. In order to get the, for minimization problem, again, lower bounds, we will be comparing our bounds against this most commonly used standard lower bounding technique for multi-stage stochastic mixed integer programs, namely the perfect information bound. So basically, you look at the future bunch of scenarios, you get a huge sample, you solve a deterministic problem for each, record the objective value, and you take the expectation of these optimal objective values to get this perfect information, namely PI bound. And for the sake of our primal policies, I will consider not a myopic, but a little bit of a better informed policy, namely this one that I already reviewed, conditional expected value policy. All right, so my first set of examples are from this famous lot sizing problem. So again, I'm not going to get into any details. I just want to show you some bounds and especially some gap reductions on these bounds. So here on the left figure, what we will call in the upcoming results as well, this thing called initial gap, which is the gap between our perfect information lower bound and upper bound is coming from, this gives you the lower bound, upper bound comes from this expected, conditional expected value type of an upper bounding heuristic. So whatever we commonly use in practice, we take those policies and lower bounding techniques, solve our models with these policies or the bounding technique, look at the gap between the two. And here you can see that we have basically up to 60% or 50% gaps between these two numbers to start it off. And here the bars are corresponding to different demand variability. So, but I don't care about the details right now. The only thing that I want to point out here is that the second part is gap reduction. So from the left figures gaps, which percentage of the gap we were able to close thanks to our combined improvement ideas. So due to these trade-offs, especially the bound and policy quality versus the computational time, I will be actually doing this mix and match ideas. The lower bounds will come from our NA-dur, the stronger one, but the upper bounds will come from the not that strong one, actually the stage-wise dual, because it is relying on a deterministic problem, which is much more efficient to solve than a two-stage NA-based dual. So policy. So that's why I will be combining the best of both worlds, and these gap reductions, which are quite significant, are accomplished thanks to both of these duals. So next up, I would like to quickly tell you this telecommunication problem. This is basically so-called RWA problem, which is from this telecommunication area, and it is the main provisioning problem in these structured backbone networks. So what this problem is about is we are given a graph, a network, which consists of a bunch of nodes, but also some fiber links. So it's not like our usual graphs. So if you have a link here, it means there are actually multiple cables in it. So you can use the same link multiple times, but not like what I did, with potentially different colors that we will call as the wavelengths in this telecommunication application. So what else we have as the input? We are given a bunch of connection requests between pairs of nodes. Say, I want to connect node 1 to node 6 or node 8 to node 2. And our main goal in this problem is to decide, given this set of connection requests, which ones to accept and how to grant those ones that we accepted. And this concept of granting a request between these pairs of nodes means provisioning a light path, which means we need to assign a path between those nodes, as well as a wavelength, a color, if you will. So for instance, from 1 to 6, we choose this path and we use the wavelength corresponding to color red. So there are some constraints on the problem. First of all, if you are choosing a path to grant a request, then you need to stick into the same color. So there needs to be this consistency of the light path throughout the paths that you assign to the requests. Second of all, there cannot be any conflict. So you cannot cross the same link with the same wavelength twice. So this is not allowed, but you can very well go through, for instance, this link here with a color of red and with a color of blue. So you can use multiple times, but with different colors, wavelengths. So what we do in this work is actually we propose the very first multi-stage stochastic programming formulation for this so-called RWA problem. And after the modeling contribution, then we are applying our Lagrangian-based dual decision rules. And we are, again, I'm going to just show you just the bound improvements. So just look at the boxes that I highlighted here. Basically, just the same gap reduction. If we had this initial gap between PI and expected upper bound heuristic values, how much of that existing gap we were able to close thanks to our Lagrangian-based dual decision rule bounding techniques as well as policies, we see that the gains could be up to 63%, which are quite significant in this highly difficult binary recourse integer mixed integer program. Okay, so the next example is this service system stuffing scheduling. It's another fundamental example problem where you have different types of customers and different types of servers with these different skills. And customers arrive to the system randomly and they are willing to wait. If there's no available server, they are willing to wait. They get into these queues, but they have a patience limit. If they wait too long, they will leave your system. So you might be losing some. So the goal is to basically assign customers to these available servers. And in that regard, we need to first of all decide from each type how many servers we should have. In other words, we have the staffing decisions. And second of all, we have these options of schedules for our people. So we need to also assign them a particular schedule. So this is staffing and integrated scheduling problem. So we had some call center examples for this problem. And again, we modeled it as a multi-stage stochastic program for the first time, and we applied LDRS. And here what we can see is this initial bounds were happen to be like this. And when we apply our ideas, then these are the final bounds for these preliminary experiments. So there could be a reduction up to 5% or so. So this is again promising in this time mixed integer recourse problem. So my final example is from a healthcare domain, which is this distributed operating room scheduling problem, which is inspired from this Toronto hospital setting here. So here, for instance, our university has a bunch of hospitals that collaborate with each other. So these hospitals actually, they share their patient list for certain types of operations, as well as their operating rooms. So now the goal is, given a list of patients with certain surgery requirements, you need to decide which hospitals and which operating rooms and which days to schedule these people's surgeries. So you get to make, first of all, these assignment of patients into different hospitals' operating rooms for a given finite decision-making horizon. But then there will be uncertainty, and the main source of uncertainty here will be about surgery durations. So as you get to observe real surgery durations, then you might realize that, oh, if I have 2 people in this operating room today, maybe one of them took much longer than anticipated. So unfortunately, we get to cancel this person today. We cannot start their surgery. So in that case, you will get to make some rescheduling decisions. So in that case, for this very patient, you can say, oh, you know what, I'm going to assign you, reschedule you now that I realize I cannot have your surgery. I'm going to put you back into this day 3. I will keep you in the hospital. Or if you realize that maybe, oh, you won't have any room later on as well, you can actually push these people to the next planning horizon. You can completely cancel their surgeries and pay a higher penalty, of course. So we have, in other words, in this model, some high degree of scheduling and rescheduling decisions under the surgery duration uncertainty. So in this work as well, we propose the very first multi-stage stochastic programming model, and then we apply Lagrangian dual decision rules. And here are some preliminary results from this work. And these are very small instances. And in fact, just to make sure that things are working well, to be able to also compare them against the exact values, these are scenario tree based instances. But nevertheless, from this first set of instances, what we observed that the actual, again, optimality gap reduction over this traditional gap, optimality gap, is up to 83%. So again, we see a lot of promise of applying these type of new decision rules in multi-stage stochastic mixed integer programs. All right, so to sum up what I have is, our main idea has been how things are started. Because we have these decision rules and we can apply them on the dual side for LPKs, why don't we do the same thing for the IPKs and consider multi-stage stochastic mixed integer programs? But this time, let's get help from the Lagrangian duals. And the key idea has been applying linear decision rules on those Lagrangian duals. And one main advantage, actually, we can say is you don't need to now limit yourself to a scenario tree type of an uncertainty model. You can get to work with sampling-based approaches, and these obtained 2-stage problems can be solved by means of decomposition, cutting plane type of algorithms. And most particularly, we actually talked about these 2 specific duals and tried to have a theoretical comparison between their strength, but also with some heavy computational results. We tried to show that they could be helpful both in terms of lower bounding as well as deriving some primal policies. And yeah, I already talked about 4 major applications, all of which showed us some improvements, significant improvements on what we could do with the traditional techniques. So we are hopefully able to do more of these and actually make better use of these decisions. Okay, so that's all I have. Thank you so very much. If you have any questions, I will be happy to stick around now or for the break.
Thank you very much, Merve, for a very nice presentation. So, any questions from the audience? If not, I have one or a few. So maybe you can talk a little bit more on the basis functions. So the basis functions are doing a lot, right? They're so but maybe I missed this detail. So how are they defined exactly?
So we have a choice. So we get to design them before we solve our Lagrangian dual problems at all. And same thing goes through for other standard linear decision rules, for instance. You need to choose them. So the most common use of them is this so-called standard basis functions, where if you have, for instance, up to stage t, these type of random variables, you just use them as they are. For instance, if you have 5 different products and you are talking about demand being uncertain for those products, you just use them as exactly what demand values I observed. These are my basis function values. But then you can make choices as I have here, for instance, demand 2 times demand 3. That's my another basis function that I'm defining that brings me extra flexibility. So you can also design highly nonlinear functions of the history, because eventually they will just return you a number and we will multiply that number, you know. But it's always good to, of course, include more basis functions so that you have all the history mapped into some granular shape. But then it means we are introducing more of these variables. It gets harder to optimize. So a few things we know about our particular stage-wise and non-anticipative deals. For instance, for the stage-wise, actually it's sufficient to use the basis functions up until your current point rather than using something from the future. Like there's some redundancy that we can talk about. We have some ideas like such simple observations in the paper. But at the end of the day, as I said, like this is very interesting for decision rules here or in the dynamic programming literature for value function approximations in the means of, again, basis functions. I still think it's a pretty open question. Like some people are, for instance, trying to use machine learning these days for especially dynamic programming to choose these options. So it's a tough call, but we only illustrate that choice is important. It makes a difference on the bound quality as well as the policy quality.
Very interesting. So there was a raised hand. Yes, Tito.
Yes.
Tito. Hey.
Hello, how are you?
Great to
thank
see
you for your great. Thank you for your nice talk and very, very interesting work. I have a question related to Walter's question, the basis function, because you had the result that the no anticipative bound is better than the dual, right? I mean, there's an existent result, right? There you said that there exists some basis functions for which this is better.
Yeah, but it's constructive.
So, so it's constructive proof. So you can find actually this find these basis functions, and are they related to the ones? I mean, if you're given a set for the stage-wise, from those basis functions, you construct a new set of basis for the no anticipative. Yes. How does it work?
Exactly. So what you do is, like, if you give me these basis functions for, let's say, the stage-wise, then we just have a addition to those. Basically, like it's also using, let me find the model maybe somewhere. So we are taking those basis functions and creating some mapping of them based on these matrices. So we basically use this information in the constraint matrix to get a transformation of them, and that information is sufficient to ensure, like we are able to basically, what we are using that I didn't mention actually, while comparing these two bounds, we are using their primal characterizations. So, and in that primal characterization, these relaxed constraints, they come back to the primal characterization in the form of an expectation multiplied with the basis functions. For instance, you take, let me, go back to the multi-stage model here. So for instance, you take these constraints and multiply them with certain basis functions, and you take the expectation, for instance, of this thing, and this should be equal to 0 for all t. So in the primal characterization, we have something like this. So that's why the intuition behind it was, oh, if I have these basis functions for stage-wise, if I use these type of options for the second one, then I can get an equivalence or mapping between the two. I'm allowed to now compare them. So basically, the ones that we built were using the original basis functions coming from the stage-wise and these constraint coefficients of our decision variables.
So you have to solve an equation that was essential to get the new basis functions. I didn't.
No, it's just the form. We just know the form of it. So for instance, if this one returns you this number, oh, now multiply it with this matrix and then this one, and then return this number. This is another basis function that we are adding to our set.
And if you use the same basis functions for the stage-wise and the no anticipative, is it possible to say anything about the relation between them?
Yeah, so I believe, so I don't recall on the top of my head exactly what we stated in the paper, but we certainly have these basic observations to compare them. And some observations as in like, oh, if you use this nested type of basis functions, for instance, it's getting better. Some obvious like redundant cases that we can eliminate. So we have some results in that regard, I believe, in the revised version of the paper at least.
I see. Okay, thank you.
Yeah, you're very welcome.
Are there other questions? We still have time.
I have one question. Hello, Merve.
Hey, man.
It's good to see you. Thanks for the great talk. So about the basis function, how much of these choice of basis function is sort of guided by the application? So you mentioned 4 different applications. Did you end up using different basis functions based on the application under consideration, or?
Yeah, that's a good question too. So definitely, I think it will be very valuable to include basis function that is inspired from your particular application. So the most commonly one that we use are just the standard basis functions, random variables themselves. So we believe we should have them no matter what. But on top of that, I think it's really important, for instance, not in this Lagrangian dual decision rule work, but for the first work that I had with Jim, the 2-stage linear decision rules, we had a capacity expansion problem from power systems. And in that work, basically what you were doing is for certain parameters, there were these, for instance, demand of a product at time t, for instance, it was obtained by multiplying bunch of other factors. So there was a demand factor. So it was, I guess, coming from Shapiro's paper, whatnot. So you had something like, say, theta, k, something like that. So you had some factors and demand was obtained. The original underlying stochastic process describing the demand had these factors, products. So in that case, actually, we tried to use these products, underlying products themselves as an option. So that gives you the demand, or you can use these guys individually. So, but we tried, for instance, these products that were directly inspired from the formula that we see for certain parameters with the hope that it will give you something better. You know, so it will be really good if you look into more carefully into your generation, the process, and maybe my intuition is if you try to at least match that, it might be good, but I think it's a little bit also arbitrary there, what might work the best.
Thank you.
You're very welcome.
So Eric has raised his hand. Eric, do you have a question?
Yeah, just if there's still time left.
Of course, we have, well, 2 minutes, but it's the break afterwards. So
yeah. So whenever I think of choosing basis function, it seems like it's the topic of this discussion right now. I think of the kernel trick in machine learning. So have you looked into how to use reproducing Hilbert kernel spaces and stuff like that here, or?
No.
Okay.
But I really hope that someone from our community will have us some answers, at least try some machine learning ideas, whatnot. So, but I haven't had a chance to get to that. Although, again, we need to try and see, right? So does it worth the effort? It's not clear, you know, because there's also this trade-off. For instance, shall we increase the basis function options in a linear affine decisional setting? Or shall we even like dump the whole LDR setting and move into piecewise linear functions or nonlinear rules themselves, you know? So after a while, maybe it's a better choice to even drop the linear decision rules.
Yeah, but the kernel trick allows you, for instance, to have the inner product with any polynomial function. So
yeah, I haven't looked at them, so I'm not knowledgeable.
I don't know what type of what would be the type of programs in the end you end up solving. It seems like it might be monstrous.
Right. I was hoping something like more like offline learning of the basis functions, and then you fix them, and then you work with the fixed forms rather than optimizing over the form of the even basis functions.
That's good.
I think something more dynamic will make more sense. You do it online, you get to learn the basis functions as you go, maybe as well.
Yeah.
Yeah, based on this discussion, I hope there will be a couple works next few years on this very topic, how to choose the basis function.
Great. So we arrive at 2. So let's have the 30-minute break. Again, thank you very much, Merve, for the
Yeah, it's truly my pleasure.
great presentation.
Thank
And
you so much.
so